most of the optimization problems I've gone over were maximization problems. Let me just go over one minimization problem. Actually, this is a problem we've gone over before, but we didn't do it formally. Okay. Consider a firm with the following average cost function. Average cost for this firm is given by this equation. And you're asked to find the minimum average cost. How do you do it? Yes. Yeah. Find the derivative. In this problem, the objective function is given to you. Now, you know what I could have done to make this problem a little more interesting? Perhaps I should have given you the total cost function. Notice the total cost function corresponding to this average cost function is just multiplied by q cubed minus 4q squared plus 8q. I could have given you this total cost function and then said, find minimum average cost for this total cost function. In which case, all you would have had to do to get your objective function was to divide both sides of this equation by q. And you would get this average cost function. Okay? So let's suppose you've got the objective function. You've got the average cost function. Then, Andra, the first order condition is to do what? Just take the first derivative of your objective function. So it would be AC prime, and I'm just writing parentheses q to illustrate that this is a function of q, is equal to what? 2q minus 4. Okay. And then what do we do with that first derivative? Set it equal to 0. Okay. And setting it equal to 0, and then we solve for q. And we get this value of q that satisfies this first order condition, and that value of q is called what? Critical value. Okay, so just solving this equation, notice we get 2q equals 4, divide both sides by 2. You get a critical value of q of 2. Okay. What next? We've done the first order condition, the second order condition. And Heather, what do we do to get the second order condition? Okay. In other words, we take the second derivative, and AC double prime of q is equal to what? 2. Okay. So what does this mean, the fact that the second derivative is always positive? In terms of optimization theory, what is this? What can we conclude? That we reach a relative minimum at this critical value of q. So the fact that we have this, let me just summarize this. We found that the first derivative at q equals 2 is equal to 0. We find the second derivative at q equals 2, in fact, at all values of q, because the second derivative is just a constant. and that is greater than 0. These two things combined guarantee that average cost at Q equals 2 is a relative minimum. Okay. First order condition, second order condition. Second order sufficient condition for a minimum is satisfied, so that guarantees that this is a minimum. And what is AC of 2? Average cost at Q equals 2. You just plug into the objective function. It's going to be 2 squared minus 4 times 2 plus 8. And this is minus 8 plus 8, 0, so it's going to be 4. The minimum average cost is 4, and it occurs at an output of 2. So if we sketch this average cost curve, it looks like this. Let's measure output on the horizontal axis and average cost on the vertical axis. The vertical intercept of this function is what? What is the vertical intercept? Diana? 8. Okay. Notice if Q equals 0, average cost will be equal to 8. So that's where it starts. Because this coefficient on Q squared is positive, it's going to be U-shaped. So it's going to be U-shaped, and if you graph it, it's going to look like this. Right here, at Q equals 2, the slope of the function is 0. That's where your minimum is. And we just calculated AC at Q equals 2 is equal to 4. So the minimum average cost is equal to 4. Okay. The fact that the second derivative is positive means it's going to have this convex shape around this point right here. Notice the first derivative goes negative, 0, positive. It's positive rate of change. Okay. All right. So there's an example of a simple minimization problem.